Okay, now fine. Okay, welcome to this new session of stochastic simulation of stochastic processes of systems biology. Today I'm going to talk about the simulation of RNA and protein dynamics. So we have been talking about in the last session about the Berthet process, that is like the standard way to simulate these kind of processes when you have a rate of production, when the number of proteins jumps from n to n plus 1 at a rate k, and the protein degradation when rates jumps from n to n minus 1 at a rate proportional to the number. So you can check here the trajectories that you can get using simulating this process. However, the main issue with this process is like the variance is always the same as the mean, because it's the main property of the Poisson distribution. So if you have, you check in the experiments, the actual data shows that the variance can have higher or lower noise than the Poisson distribution. So one way to check this or to change this problem is coupling the RNA and the protein. Yeah, so we can check our previous script for Berthet process, like doing quickly. So we can simulate here trajectory with mean 10. And you're gonna get something like this. So the relative fluctuations are relative high, but if you do the same and increase the mean, you can check that the relative fluctuations are less than with 10 proteins. If you increase even more to 1,000, the relative fluctuation are even less. So in the beginning of the systems biology, they expected like the proteins show low fluctuations in the cell because the number of proteins inside a cell is thousands or tens of thousands. However, as I told you, the discovery that these proteins can actually fluctuate started a new field of stochastic simulation, where because the stochastic fluctuations of the proteins are relatively important. So why the proteins have such a high fluctuations? So the answer comes from the central dogma of this molecular biology. So the information of how to produce a protein comes in the DNA. Remember that depending on the order of the nitrogenate bases, the cell can produce different amino acids, and it comes in a chain. And using enzymes like the RNA polymerase, the cell produce molecules called RNA that are cells with only a single strain, as you can see, like the DNA has double strain. And the number of RNAs fluctuate, and the number of RNAs is around 10 or 20. So given this low number of molecules inside the cell, the random fluctuations of the RNA are relatively high. And then using this RNA, there are another kind of enzymes called ribosome that binds into the ribosome and produce the proteins. However, this RNA usually is a very unstable protein, stable molecule, and the lifetime of them is approximately in order of a couple of minutes. So this RNA usually is a very short-lived protein molecule, And the proteins, on the other hand, they are very like relative long-lived. So those are the main difference, and essentially, like the noise of proteins can be related to the noise of mRNA. So how is the idea? So the idea of the model is proposing a birthed process, but now you're gonna have four reactions. The first reaction is the production of RNA. We're gonna call here the RNA-R that occurs spontaneously at a rate constant, Kr, that can be also an exponential distributed event. And in this reaction, the number of RNAs increases by 1. Also, the RNA degradation occurs at a rate, in this case, proportional to R, and with a constant gamma R. Gamma R times R gives you the rate at which the RNA jumps to R minus 1. And the protein synthesis, as you can see, the rate is also proportional to R. So the more RNA molecules you have, the higher is the rate at which the protein is produced. And the protein degradation is proportional to the number of proteins. And is the rate at which the protein is decreased by 1. Okay, so it's going to be like the same thing as the birthed process, but in this case, you're going to have 4 reactions. Okay, so we can like use the same script for birth, but now we're going to have 4 reactions. So in this case, I should, because the number of reactions are so high, so to me, it's going to be better to make a function that calculates the number of the time for the next reaction. So we start here, import the typical libraries, pandas, tqdm, numpy, and matplotlib, pyplot. And this was my the script I developed in the previous session. So remember what it consists on. So first, we're gonna have as arguments our rates. So our first rate is the rate of RNA production. We're gonna call it Kr. The next one is this gamma R, then Kp, and then gamma P. Okay, so let's call gamma R GR, Kp is Kp, and gamma P is Gp. Our time max of simulation, maximum time of simulation, and our state, let's call it R for RNA and P for protein. Okay, so we have 4 reactions. So we define a new function called, let's say, get next time to reaction. So here we have like an issue. I'm not sure if it's bad or good, but we have here 4 different cases. The first case is where all these 4 things, or R and P, are different than 0. So this rate is some finite, has some finite value. But if R is 0, this rate is also 0. So the time to next reaction, if you use the Gillespie formula, is going to give you infinite. But it's going to give you some problems in the simulation. But so you have to consider all the cases where R are P and P are 0. Okay, so let's do it more explicitly. So if R is different, remember different, you use this symbol, and P is different than 0, your rates are the same, no? So we have to calculate 4 different times. Sorry. T1, T2, I'm just copying, and then I'm gonna change. Okay, T1 is gonna be the production of RNA. So this occurs at a rate Kr. So remember 1 over Kr times the natural logarithm of a random number between 0 and 1. The second one occurs at a rate gamma R times R corresponds to the RNA degradation. And this one is RNA synthesis. And the third is the protein synthesis. So this protein synthesis is Kp times R, the same. And the fourth is the protein degradation that occurs at a rate Gp times P. So the other case is where, let's say, R is 0. If R is equal to 0 and P is different than 0. So we have that this rate, 1 over this rate is infinite. Yeah, so like the infinite doesn't make sense in numerically, so we can add like a very big number instead of infinite, and the same for this. Okay, so next, in the next scenario, let's say P is 0 and R is different than 0. So these rates are correct, but this guy is infinite. And in the final case, both of them are 0. So here is elif. Remember this other option different than if, no? You use the elif. Loop. So if both of them are 0, it can be else, no? Because there's no more options. This guy is infinite. This guy is infinite. Positive. And the only thing that is happening is the RNA synthesis. Now, after calculating this 4 times, I select the minimum. Of them, and this remember that these are inside this function. So this function is gonna return your time, the minimum time, and the reaction kind. Okay. Now, what do we do? So first we calculate the next time to reaction. So now this is like the actual algorithm. So we calculate our time to reaction, calling this function. And here I did the same, no? But if my time to reaction is less than my maximum time, I propose a new like temporal time, such as is the time for that has been passed during this reaction? Or it's like the time that is gonna pass after the reaction. So if my time is higher than Tmax, or while Tmax is greater than my time to reaction, I check which kind of reaction is the one that I got here. And so all of this, I think we checked in the previous session. You can check the video better. So we have different possible outcomes. The reaction is 0, the reaction is 1, or the reaction 2 or 3. So if my reaction is 0, it means that the minimum is T1. So T1 corresponds to the time for RNA synthesis. So if react is 0, there's a RNA synthesis. If my time is 1, the reaction is RNA degradation. If the minimum is T3, protein production, else protein degradation. Okay, and we calculate again the next time to reaction after performing these reactions. And this evolve gives you RNA, R, and protein. Okay, it looks fine. So I also copy paste the script for simulation from the previous script. So I have to define different the different rates. Okay, so we come back here and we check the following. So there are many kind of different ways to estimate the moments or like the expected values of the protein and RNA. I won't go deep on these kind of methods. Probably there are some theoretical tools. Maybe we can discuss them later. But the idea is the following. Given these rates, KR, gamma R, KP, gamma P, you can show that the mean of all of them depends on the rates. So the mean RNA is going to be KR over gamma R in a similar way that for the Berthoud process, the mean in a steady state, that means with time going to infinite is K over the dilution rate or the degradation rate. So the same, the mean of R is the production over the degradation rate. And the mean is the same times Kp over gamma P. So one way to estimate these rates are estimating the gammas. So usually the gamma P corresponds to the growth rate. Because as I told you, the proteins are relatively stable compared to the cell growth rate. So most of the degradation events of the protein are actually dilution of the concentration. So gamma P is approximately the growth rate. Sorry for my handwriting. And gamma R is something about minutes. Or I mean, the lifetime of RNA is minutes. So let's call it let's say that the growth rate is 1. So gamma R is going to be around 10 times gamma P, because the RNA dilute is approximately 10 times faster than the growth rate. And as I told you, the expected value or number of RNAs inside a cell are 10 or even less or even more, but no more. The particular number is around 10. And for proteins, we have that this number can be around thousands. So with this idea, we can like estimate the KR, no? So if expected value of R is 10 and the gamma R is 10 as well. So it means that KR is approximately 1. No, sorry, is 100. So we have this, we have only KP, no? So KP we can solve from this. So if KR over gamma R is R steady state, that is 10, and gamma R is 1, gamma P is 1, we have that, and this is 1,000. So KP is 10. So we can start with this kind of approximated rates given the typical numbers. Okay, so gamma P is 1, gamma R is 10, KR is 100, and KP is 10. We start from R equal to 0 and P equal to 0. And the total time for simulation is, let's say, 10. I'm gonna get data every 0.01 units of time and starting from t equals 0. So I'm gonna save the data in an array that is gonna have the time, the number of RNAs, and the number of proteins. And the RNA and proteins, I'm gonna get it evolving the system using the script. So KR is KR, GR is GR, KP is KP. Tmax now is gonna be my DT because I'm simulating the system every DT and export the data in this array, and the rest is the same. If I was right, it should work. And I convert the array into a data frame of pandas. So the first column is time, the second column is RNA, let's call it R, like capital R. And the next is protein. So for these pandas or data frames, it's common to use a capital letter in the first letter because usually like the normal letters are for functions, and these capital letters in the first usually are for the variables of the. Okay, so let me see. So we can plot the RNA. So our RNA has a mean of 10 and this expected high fluctuation. Let's see what happened with T protein. Let's call it P. So here the mean is 100. So then yes, so it has to be 100. Sorry. Okay. So you see like high fluctuations compared to the previous case where as like a molecule with 1,000 like expected value of 1,000 has fewer fluctuations that this case where the noise in the protein comes from essentially from the RNA. Okay, so we can check and perform this for 1,000 cells. Let's see. Let's say. So again. So I'm gonna do this for let's say 100 first cells. So I'm gonna use here TQDM that gives you approximately the time you're gonna spend on the simulation. So I perform the same. But here I have to start with an empty array for data. And I'm gonna save the first, like the initial value before starting the simulation. So I add I that corresponds to the label of the cell. And I save the data every time I evolve the system. So you can see here, like this takes like a couple of minutes. So the question here is like, this takes time because when you have 1,000 of like molecules, the rate of degradation is gamma p times p. Gamma p is 1 and p is 1,000. So it means that in a particular time interval from 0 to 1, you have approximately 1,000 of events. So 1,000 events every unit of time times 10 is going to give you 10,000 events every like simulation. So the number of events can be so high that the problem with the birth process in this case is like the time that it spends can be relatively high. That's why I started with 100. And the other thing is like for having a good statistics, you usually gonna need around 1,000 or 10,000 samples. So this is gonna give you some troubles when you want to perform some more difficult simulations. So I'm gonna show you how to overcome this problem later. Okay, let's say we finished and we want to calculate the mean of R and the mean of proteins. So here again, I check that I have first to convert this guy into a data frame. So I'm recopy pasting the previous session. So it's gonna give you, the first one is gonna be cell, the second is time, the third is RNA, and the fourth is protein. And let's save it because this takes time to to run again if I make a mistake. So the app sells to CSV. Remember, CSV corresponds to comma separated values. So it's a file where I'm going to show you where each element is separated by comma. It's gonna be I don't know, R versus P, CSV, and the index. So usually, like the data frame, have this additional column called index. So this index gives you like the number of the row. So if I save it the standard, this is gonna save this row that personally I don't care. So I put here index equal to false, such as when I read this file again, it doesn't have the index. Let me show you like more detailing. So let's say I save this guy without with index, so I can read this guy. So I use the function read CSV. So this has an additional column that is we won't use anymore, and it has its own index. So the index is not useful. So next time when I read without the index, it doesn't have this index. Okay. So we read the file, and for all the time in my data frame, I select all the rows such as the time is time, and I calculate the mean, the variance of R and the mean of variance of P. Let's call it here R and here P, like to differentiate them, like. And I'm gonna save MNTR and variance of R, mean of P, and variance of P. And I save it in as a data frame with mean R, with columns mean R, bar R, mean P, and var P. So this takes a little bit of time. So it gives you like the mean and the variance of the distribution over time. So we can plot it. The time in X and the mean, let's say R. So you see like the mean is very stable on 10 as we expected. The mean P is like goes unstabilized over 1,000. And the variance of P, that is the one that we are interested on. We have to compare it with the formula, no? So here you see like these random fluctuations. This is because like the number of elements is only, well, number of cells is only at 100. So we need approximately 1,000 or 10,000, but it's gonna take 10 minutes, so I won't risk. So we can compare with the formula, no? The formula is this thing, no? So what's the message here? So this guy, this case over gammas are mean P. So you can check that if this process was Poisson, the variance is just P. No, remember that for a boson process, the variance is P. However, here the solution gives you an additional term here, Kp over gamma R plus Kp, that can be like using these values can be redefined using and written by this way. Okay, mean P, mean R, and gamma P over gamma P plus gamma R. So we only need like the particular lifetimes of proteins and RNA to check like this how important is the noise of RNA in the noise of the protein. What's the trick here? Usually the RNA is very faster. So this guy is approximately gamma P over gamma R. Okay, and we know that it's approximately the P is 1,000 and R is 10. So this guy is going to be 1,000 over 10, and let's say gamma P is 1 and gamma R was 10, no? So this gives you, oh no, this is 10. This gives you approximately 10. So this term is 10 times bigger than this. Yeah, so this term in some cases is very important, more important than the intrinsic noise, that is this one, and this is the transmitted noise that comes from the RNA. Okay, in the particular case, for instance, where the RNA is very stable, this guy is approximately 1, and you have that this is P over R. Yeah, anyway, that like this noise of RNA is kind of very important. Okay. Yes, so in our case, how much is this? We say that this is 10. So this is approximately 11. So the variance of this is going to be 1,100. 1,100. No, is it? Times, okay, in our case, how is this? Let me do it fast. P is going to be expected value of P times 1 plus P is 1,000, R is 10, gamma P is 1 plus 10. So let's say this is 1 over 10. It's going to be 10. Expected value of P times 1 plus 10. It's going to be approximately 11,000. Yeah, that's the thing we see here. Yeah, the variance is approximately 10, 11,000, but with more samples we can check it. This is approximately 10,000. Okay, so how can we make it this faster? How much time do we have? We have enough. So one approximation, like to make this simulation faster and like avoid this reaction, sometimes we only need the protein. We don't care about the RNA dynamics. So one way to make this simulation faster is propose the Bohr solution process. So what's the idea here? The idea here is like sometimes the RNA is so short, the lifetime of the RNA is so short that every time RNA is produced, multiple proteins is produced, and the lifetime is relatively short to the protein. Okay, so in this case, we can assume that every time an RNA is produced with a rate, let's say in my case was KR, but in this figure was KX, but let's call it KR. my protein, that in this case is X, increases by a number B. This B can be a random variable or can be a fixed. Let's start with a fixed number. And between different bars or different like protein productions, the protein is diluted continuously following an differential equation. This gamma can be constant. So essentially this is gamma P times P or X in this case. And a particular trajectory of this event is like this. So different bars and continuous dilution between bars. Okay, so how can we simulate this process? So this is kind of like a particular case. So unlike the Berthet process, here you see like there are some continuous dynamics of the protein. So now we are working here with the concentration. In the previous one, we assumed that protein is proportional to concentration. So the protein has integer numbers, 1, 2, 3, 4, 5, etc. But here, the protein is a continuous number that can get any positive real number. So since it's a continuous, you can define like exponential degradation on it. Okay, so we simulate the time to reaction as a simple Gillespie formula or an exponential variable with the rate k, and we check our next time to reaction. In the first case, the next time to reaction is bigger than my exporting time, so I have to dilute the protein until this point and export this value of protein. Okay, if the reaction is on one or more reactions occurs from 0 to my Tmax, I perform all the reactions until the next time to reaction is greater than, or like the sum of all the time of reaction is greater than my Tmax. In that case, I evolve the system till Tmax and export that value. Okay, so I have here the copy. Can check it more carefully remember that in the repository in the description of the video is going to be this script, so you can check it more carefully. So here is the script. So I'm going to explain you more or less. Okay. So we define Tmax. We already have to give it the next time to reaction. Remember, it's going to be like this remaining time. If I restart a new reaction, they're going to give it. I have to give it the time to reaction as a parameter. So if my time to reaction is higher than Tmax, that corresponds to the first case. Time to reaction is this guy. If this guy is bigger than Tmax, I have to evolve the system. And my time to reaction is decreased by Tmax. That means that before the reaction, I had this time to reaction. Now, after like exporting, I have this one for the next iteration. Because already a time of Tmax has passed. And my protein is gonna get degraded by like following the exponential trajectory. Otherwise, I start like to perform the reaction. So while my TT corresponds to this to the like T max minus every time, so corresponds to this. Then the next iteration is going to be this, and the next iteration is going to be positive. So you can I explained this in the previous session, so you can check it. So while this TT is greater than TR, I perform the dilution, and if when the reaction occurs, I increase my bars. Let's start with a bars of 1, and I calculate the next time to reaction using the GLSP formula. And then I let the system pass and perform the dilution. That means in this case, no? So here in the slash reaction, this next time to reaction was greater than Tmax. So what I did was I calculate this T, that was my TT here, that is essentially Tmax minus T1 minus T2, corresponds to this TT. And during this TT, I let it degrade and export that time. Yes. And I export the value of the protein. This is, yeah. So the same script for simulation, and I export the data, and we're gonna see something like this. Here's just a question. Okay, so to those people who have to go, don't worry, we're gonna upload the video soon. Okay, so you see something like this with this particular case. So let's do it with, and you're gonna see something like this: degradation, jumps, degradation, and I have this theoretical calculation. So how to do it? So usually we can use the moment dynamics approximation. Okay, so how that's consistent? So remember that in the previous sessions, we calculate like the time evolution of a particular moment of my variable using this formula. So for the Poisson process, I need the value of this system after the jump. In this case, this was like production, so the jump was +1 minus the value before the jump, n, to the value alpha. If its mean is 1, alpha is 1. If its second order moment is 2, and so on. This was the gradation, so the value after the jump is -1, so you have n minus 1 here. But in this case, the value of the jump after the bars is b. This b can be also a random variable with a given distribution. Here you have also the continuous dynamics. So this continuous dynamics has to have here a minus, but is the derivative of x of my moment alpha. So in this case, if it's 1, is the derivative of x, so it's gonna be 1. But if it's alpha is equal to 2, the derivative is 2 times x times the this derivative that is minus gamma x. Okay, so we can show that, well, this is 2 here. We can check that these are the solutions for the steady state moments. For getting the steady state moments, what we have to do is to set this guy, the derivative, to 0 and solve it. Okay, so for instance, for the first order moment, you're gonna have the xdt equal to value of expected value of k x plus 1 minus x. This guy is simply expected value k, expected value of x, and this guy is plus derivative of x is 1 minus gamma x. So it's gonna give you. Oh no, sorry. This is k. This is only k because x and x cancels out. And this was instead of 1 is b. Minus gamma expected value of x. So if you make this equal to 0, you have that the expected value of x is k b over gamma. And the same you can check with the variance. Okay, so quickly, I'm gonna estimate, like do it for 1,000 cells. So you can see like this took already 8 minutes compared to the other. It's like approximately 10 times faster. So I can okay, so I simulate 1,000 cells here for estimating the moments of the process, and I can show you using this guy how is the mean and how is the variance. So the mean is 10. Let's say here I use as a parameters k equal to 10 and g equal to 1. So compared to the values, k is equal to 10 and gamma is equal to 1. And the burst here is 1 because I'm increasing the protein by 1 every time the reaction occurs. Okay, so this guy is also squared here. So when one variable is deterministic, it means that it's not a random variable. Usually, as I told you, b can be a random variable. So if it's a random variable, the variance of that variable is different from 0. When the variable is deterministic, it means that when it's not a random process, the variance of b is 0. It means that the b squared is the same as the expected value of b squared. Yeah, so in this case, if b is deterministic, this variance is simply k over 2 gamma expected value of b squared. So if this guy is 1, the b squared is 1 as well. No? So it's going to be k over 2 gamma. So compared to the Poisson distribution or the Poisson process, it has a difference. It corresponds to this value of 2 here. Remember that for the Berthet process, this guy is the same as the mean. Yeah, so this has this value of 2. So essentially, this system is less noisy than a Poisson process. That's the main issue. So if you check here, the variance, this doesn't go to 10, that is the same mean, but to 5, that is the mean over 2, as we observe here by this factor of 2 here. Okay, but overall, we can overcome these problems and use these kind of systems to simulate the protein. Okay, so we can check like the bore size, such as the mean of the protein is the same as this mean. So the idea is like we check, we rewrite the system such as the system has the same mean and the same variance of this protein RNA system. Okay, so in this case, I'm gonna use K as KR and gamma as gamma P. Okay, so if I want the same mean P, I already have KR and gamma P, so the mean bore size has to be KP over gamma R. Such as I have something like similar to this. So I'm gonna call this the mean bore size. And the interpretation of this guy is that Kp is the number of proteins per unit of time per RNA, and gamma R is 1 over the average RNA lifetime. So essentially this word is the number of proteins done by RNA, but by the number of like the time that an RNA lives. And we can also like compare this formula of the variance of X with the compare it to the actual value of the variance of P. Yeah, so this has to be KR over gamma P over 2 times the second order of my burst. And so you can estimate the second order moment of B, such as it satisfies this equation. And the solution for this is simply this. That gives you the CV square of the burst. Remember that the coefficient of variance square of the burst corresponds to the variance of the burst over the burst squared, or the mean burst squared. And why do I need the CV square? Because given that this CV square is arbitrary, I mean, can have any positive value. We have to model it using gamma distributions. And remember that gamma distributions needs the mean and the CV square of the process. So here I had like prepared it. No. Okay, let's do it fast. So we can. So the main change we have to do here is like make B a random variable. So let's use the evolve. I'm gonna do this quickly. So as a parameter, you're gonna have protein, the mean B, and the CV square of B. So remember, mean B is gonna be KP over gamma R, and CV square of P is gonna be this guy. Two for gamma p over kr times p squared times the variance of p minus 1. So, and remember that the variance of p is the expected value of p, that is 1,000 times 1 plus 1,000 over 10 times 1 over 1 plus 10. Okay, so every time a burst occurs, I'm gonna set instead of 1 random gamma with a scale. Remember, the scale is gonna be the mean times the CV square, and the shape is gonna be 1 over the CV square. Um, hmm, okay. This is gamma p. No? KR p or p. And this is KP comma R. Mm-hmm. More piece teaser. And okay, we simulate one trajectory. using our parameters, and we can check the typical check. One second. So here KP was 1000. Okay, I'll check this more carefully and I send you this script. There's something difficult, and I compare this with the data again. Thank you very much, guys. That's everything I wanted to show you. So see you guys next